So hello everybody. We have here in the Institute of Geoscience the Professor Lee. He will give a lecture about the reactive transport of trace metals and organic contaminants in coastal wetlands and watersheds. So we welcome you here and thank you very much for this lecture. Okay.
Thank you. Thank you for having us here today. It's absolutely our great honor as an opportunity to give a research presentation at the top geoscience institute, not here, just here in Brazil, but as well-known institute, Geoscience Institute. So my research talk today is going to focus on the hydrological and biogeochemical cycle of trace element, organic contaminant in coastal aquifer system. And so I'm going to divide my presentation into two different parts. The first part focus on the trace element, and especially focus on natural and human-induced arsenic in groundwater. So in this image, you can see that in underdeveloped countries such as Bangladesh, large population, more than 10 millions of population are exposed to high level of arsenic in their drinking water. And so you can see the image here, people just hand drill the well into the shallow aquifer. You can find hundreds of ppb of arsenic. And also, even in the developed country in US, we also see a human-induced arsenic. Example you can see here is the pesticide, arsenic-rich pesticide has become more and more common. So we have funding from the U.S. National Foundation, also the private industry, and so you can see the image here. This is essentially the research tried to remove dissolved arsenic in groundwater. So we kind of prove concept. So you see here those biogenic, very small crystal with a high surface area formed by natural sulfate reducer. They can remove dissolved arsenic by absorption and co-precipitations. And so this type of research is very important for industry, also for the community. And so exactly what are the redox geochemical control for the mobility and concentration of arsenic in groundwater? So here we use the data from the Bangladesh fluvial and coastal aquifer. And so what you see here is we have for the y-axis is the EH, is the redox condition of the groundwater. So the positive EH means oxidized condition. And the negative EH means aquifer is under more reducing condition. There's a lot of free electron. And so we see that the level of arsenic, if you looking at the shallow oxidized zone, you can see the concentration is low. So the drinking water standard for arsenic is only 10 ppb. So for this part is somewhere over here, only like here is expressed in terms of milligrams per liter, only 0.01 milligrams per liter. So the level of arsenic in oxidized zone is relatively low. And for the, you go to the more reducing condition, sulfate reducing zone, the arsenic level is also very low. So the reason in the oxidized zone that you have low arsenic because arsenic is absorbed by the iron oxide under oxidized condition. Under sulfate reducing condition, arsenic is removed by iron sulfide by absorption. So in this map, you can see that the hotspot is under moderately reducing, also known as iron reducing condition, you can see that the arsenic may reach several hundred ppb. And so this information allow scientists and also the community focus mainly on this moderate reducing condition. And another interesting topic is how climate change and sea level affecting arsenic level in this aquifer system. So here we plot arsenic concentration as a function of depth. Again, this is data from the Bangladesh, most affected country. And so you see a very interesting pattern is that in the deeper Pleistocene aquifer, the arsenic level is low. But you go to the shallow Holocene aquifer, again, you can see an elevated arsenic concentration. I think the reason is that because during the cold Pleistocene glacial periods, the water was locked as ice and glacial in the mountain. So this will lead to a global low sea level stand. When you have a low sea level stand, high freshwater table in the coastal system is going to create a very strong hydraulic gradient and very rapid hydrological flushing. So it can flush out those geogenic arsenic. Now, as the climate warm up into the Holocene, into the modern time, ice and glacier will melt. So the global sea level will rise. So when the global sea level rise, so the hydraulic gradient between the freshwater system and the sea level, you will be looking at a very gentle hydraulic gradient and very sluggish hydrological flushing. So this allows the arsenic level to build up. And so so to prove this concept, we model how fast, how many years, how long it takes to the fresh water to flush out the arsenic in the aquifer. So the model is very straightforward. Here we have a 1,000 meter long aquifer. Initially, arsenic concentration is 300 ppb. Okay. And so we solved the one-dimensional solute transport equation, assuming here we have a freshwater recharge, freshwater flush through the system. And so the diagram here shows again, along the 1,000 meter aquifer. And so the fresh water is pushing through the system from left to right. So this breakthrough line just shows the front of fresh water push through the system, flush out the arsenic. So given flow rates about 0.1 meter per day, it's going to take several thousand years just for the fresh water to flush out all the initial load of arsenic. If the velocity of this freshwater flushing become lower, it's going to take a longer time. So unfortunately, if you look at this sluggish hydrological system for most of the fluvial and coastal aquifer, again, it's controlled by the difference of sea level and the freshwater table. And so this diagram shows the global average sea level since 1900, based on the data collecting from the ocean tide gauge, and also more recently from direct observation from satellites. And you definitely can see a continuous trend of sea level rise. But since late 1990s, the sea level rise has accelerated. And so that means that this global sea level high probably will maintain the current course. So we're going to continue to anticipate very slow, very sluggish hydrological flushing. So the problem is probably going to get worse. And so essentially, we can use a very simple hydrostatic balance or more sophisticated numerical modeling to predict the freshwater saltwater interface or the front of the saltwater intrusions based on this either simple or more advanced numerical model. And so say, for example, if you know the freshwater table HF is certain distance above the sea level, you can predict this freshwater saltwater interface is located about 40 times the freshwater table. So I got a phone call from a coastal community asked a question, because of increasing water demand, I want to drill a well to meet the demand. How deep I can drill? Definitely we don't want to drill into this salty groundwater. So this simple hydrostatic balance tell us you can drill about 40 times in terms of the depth, 40 times the freshwater table relative to the sea level. And so this numerical simulation shows that if you have a tropical island surrounded by the oceans, and so if you have a freshwater table it's about 3 meters above the sea level, in the center of this island you can drill down to 3 times 40 is about 120 meters. So this is a global issue affecting coastal area, tropical islands. So let's circle back to arsenic, not just because we consider the flushing, but also we need to consider what's the geochemical consequence of, because the saltwater intrusion, you're going to see the seawater invading into freshwater bearing aquifer. How is it going to affect the mobility, the level of arsenic? And so we use the geochemist workbench. Again, this is a very popular geochemical modeling tool. I work on this software since I was a PhD student in the early 90s. Has evolved so much. I can do all kind of water rock interaction, mixing, biogeochemical reaction. But for this study, we use a well-known surface composition model to model. We're going to focus on desorption of arsenic from the surface of iron oxides. So this model simulates the surface, pretty much the surface sorption of dissolved ions onto either a positive or negative charge mineral surface. And so initial system, we have fresh water contain a small amount of dissolved arsenic. But under oxidized condition I mentioned earlier, most of the dissolved arsenic is absorbed by the iron oxide. So you see a high concentration of arsenic associated with iron oxides. Now what we try to simulate is two geochemical effects accompanying salt intrusion. One is the pH. The other one is the ionic competition. So the conceptual model is because the pH, seawater has a high pH. So that means that if you have iron oxide, you have a seawater invading into the aquifer, the surface will become negative charge. And for arsenic speciation, for example, for arsenate, which is a negative charge anions, once the sorbing surface become negative charge, they don't like each other. So conceptual model is that we're going to anticipate desorption of arsenic from the surface of iron oxide. But how much? We try to quantify. The other one, potential geochemical consequences, ionic competition. Because in the seawater, they are also negative charge ions. Example such as sulfates, bicarbonates, phosphate. I know there are some ongoing research for phosphate in this department as well. And so the main reaction we try to simulate, again, geochemistry workbench has a comprehensive database, has hundreds of species, and we can model, because each dissolved chemical species can shake hand, interact with the soaping surface here, which is, so here showing iron oxide, and they provide a soaping surface for arsenate. So for this reaction, it's a desorption of arsenic, accompany the seawater intrusion. When the pH increases from 7 to above 8.5, you can see substantial desorption of arsenic. And it's because high pH is going to drive the desorption reaction to the right-hand sides. And so our computer model predict that additional several hundred ppb of arsenic will release, become mobilized just because of the saltwater intrusions. And for ionic competition, I mentioned that sulfate, seawater has a lot of sulfate, bicarbonates. And so phosphate can come in from fertilizer, nutrient as well. They all compete with arsenic. And so the computer model tells us that there will be probably a few tenths of ppb of arsenic may be immobilized because of competition with all those negative charge anions. And so for the first part, just quickly summarize. First of all, hydrological effects affecting the reactive transfer of arsenic is, again, from Holocene to the modern time. Again, because of global high sea level stand created a very sluggish hydrological flushing in the aquifer system. That explains why we see an elevated arsenic concentration associated with a lot of coastal fluvial aquifers. And geochemical effect because of high pH, because of ionic competition, and we're going to see additional desorption of arsenic from the surface of iron oxides. So again, the first part we focus on a major environmental health issue, impact the human health, focus on arsenic. And so for the second part, I'm going to shift the focus to organic. And we're going to use Deepwater Horizon oil spill. The lesson learned from this is one of the worst environmental disaster related to oil spill in the US. Okay. And so in this image here, you can see that, so this specific incident released 5 million barrels of oil into the Gulf of Mexico. So you can see a huge oil pool. And so the BP essentially paid billions of dollars to help repair the damage for the ecosystem in the Gulf of Mexico. So the funding here was provided by the BP and also the NSF. And so the image here, you can see, you can go to this YouTube to watch the video capture. But here, you can see that the spill oil, of course, can reach the coastal area, watch the shores. So here you can see, so in the northern Gulf, we have beautiful sandy beach. Okay. So you can see that, so this is the tarballs deposits when this spill oil watch the shore so those sugar white beach consists 99% of quartz. Okay. It's easier to clean up this. The reason is because those organic compounds they don't react, they are not absorbed by quartz, our silicon minerals. So our research, we focus on the left-hand side. This is a coastal wetlands. And so we don't worry too much about the contamination on the sandy beach. And instead, we focus on this coastal wetland for a couple of reasons. And this is a very difficult environment to gather the samples. And so those coastal wetlands is ecologically important. They provide natural habitats for a lot of wildlife, fishes. And so those coastal wetlands have a lot of natural organic matters. Those are hydrophobic. They don't mix with water. They are non-polar. But those natural organic matter can absorb the spillover. And so the previous study has shown that once this coastal wetland, once they've been contaminated by spill oil, the spill oil can stay there for decades, if not longer. The main reason is that natural organic matter absorb those spill oils. So the main question we try to address, again, we try to answer the question, what happened to those crude oil once they reach contaminate the coastal wetlands? So the second question we try to address again is once we see the inflow of organic contaminant, what happened to the trace elements? And we also work with environmental microbiologists to see how the inflow of oil affecting the natural microbial community in terms of the function and the diversity. Again, the hypothesis is that the crude oil, of course, is toxic to most of the microorganisms. However, they are certain natural microorganisms. They can not only they can survive, they can thrive, and they can degrade this inflow of oil. So in other words, we anticipate the inflow of oil would reduce the diversity of the microbial community. And so the main objective is we go to, we sample, I think more than 10 different coastal wetlands, including, so you see the red color here is the worst affected area in southern Louisiana. We also sample from Mississippi, Alabama, kind of in between intermediates. Also a few sites unaffected. So we have a range of sampling sites, range from very heavily contaminated to unaffected sites. So we can compare looking at both microbial and biogeochemical consequence of the oil spill. And so the image on the upper left corner is one of the worst contaminant sites in southern Louisiana. You can easily see the oil in the open water. So this project funded by NSF, so after 9 months after the oil wash ashore, we conduct our sampling. And so 9 months after the oil wash ashore, we don't see any visible oil in the water. It probably means most of the oil in surface water has been evaporated, okay, or degraded by microorganisms. But we can still smell the chemical odor. And you can see the wildlife, the large fish-eating birds return to the system. But nevertheless, you can see this still oil suppress and kill a lot of grass and natural vegetations. And so at each study site, we recover 8 different cores, about 30 centimeters long. And so this type of research, we also conduct the surface water, essentially near the water sediment interface. And so for this type of research is not easy because certain chemical parameter we consider as redox sensitive. So when the temperature change, the EH change, and this parameter, the chemical quality will also change. So that those sediments has to be quickly returned to the lab to process in anaerobic grub bag. And so you can see the picture here. We section this sediment core every 3 centimeters. So we'll be able to look in at the variation of this different chemistry we can look at the depth profile. And we centrifuge separate the pore water with the sediments. And our specific interest is the reduced ferrous ions, also the hydrogen sulfides. So those are the very important products produced by 2 types of natural microorganisms. The microorganisms capable of reducing ions and also reducing sulfates. And I mentioned earlier, I don't expect you to read this table. Each site, we recover 8 different cores for different geochemical analysis, including elemental, total organic carbon, trace element. We also fingerprints using geochemical method, fingerprints the source of the oil, and also to study the transformations of those organic compounds. And so first of all, the dissolved organic carbons. And so you see a typical yellow-orange color of the pore water we separate from oil contaminant sediment. And this indicates very high level of dissolved organic carbon. And so you can see in the lower left, we compare the DOC of heavily contaminated site with unaffected site. So you can see that this is several hundred ppbs of DOC. Yeah. So off the chart. But for the typical coastal wetlands, the DOC is probably less than 50 ppm. On the right-hand side, here we plot the DOC as a function of depth. So surface water is above 0 is the surface water and sediment interface. Okay. So we see a pattern here is that we definitely see a notable increase of DOC with depth below the water sediment interface. So this suggests that the contamination is not limited to the surface water. They go to the deeper sediments. And you may be able to see that the DOC is lower near the surface or surface water sediment interface. We think this is because the oil, spill oil in the surface water or near the interface, probably a lot of oil has been evaporated or degraded by natural microorganisms. And now we look at the sediments for the solid total organic carbon contents. Similar story here. Heavily oil site and unaffected site, you can see that the total organic concentration reached 20-30% off the chart, never heard of it. Essentially, the analysis damaged one of our total organic carbon analyzer. Concentration is so high. Okay? And so you can see a similar pattern here. Again, for the organic carbon in a solid sediment, you can also see a elevated concentration at the depth. So the DOC and TOC just serve as a general indicator, indicate the level of contamination from the oil spill. And we, of course, we also try to fingerprint the source of this extracted oil. The reason is in the Gulf of Mexico, there are many, many oil spill incidents naturally. So how can you point a finger to the extracted oil from contaminated sediment is point to the original source in the deep water portion of the Gulf. So we use the GCMS run at a full scan mode. And so you see we compare the initial BP crude oil versus those degraded oil extracted from the sediments. And for the initial crude oil, again, each crude oil sample, you probably see hundreds of different organic compounds. But this original BP oil is dominated by the light compounds. On the right-hand side, again, this is a degraded oil we sample 8-9 months after the oil spill. You can see that this is enriched more in heavier compounds. And so the interpretation is that most of the lighter compounds, again, is probably has been evaporized or degraded by natural bacteria. But this, you cannot take this, or the local community still cannot take this to the US EPA because these two GCMS spectrum look so different, right? And it's because of the natural chemical weathering alteration of the initial crude oils. And so we run the GCMS, we target special biomarkers running under single ions. So the biomarker are the special organic compounds. They do not change much by environmental alteration, weathering, microbial degradation. That's why the oil industry has used this for a long time. They can use a specific biomarker to trace or correlate oil in the reservoir to the original source rock. And so this is nothing new. And so here we target special biomarkers associated with hopane terpenes. And so here 4 spectrum compare the BP initial crude oil, degraded oil from the plants, on surface sediment and the deeper sediments. So when we first look at these results, we kind of disappointed because they all still looks different, right? However, my biogeochemist colleague told me that we need to focus on this small spike. So those are special parameters associated with biomarker. And we were told we should calculate the ratio of those special parameters. So we compare, again, with the help from our colleague, we calculate the ratio of this specific parameter compared to initial crude oil, weather oil collected from plant sediments, and shallow versus deeper sediment. You can see that this ratio they match closely with each other. And again, we target many different those biomarkers. They all show very consistent this this specific biomarker parameters. So this gives us confidence that the weather oil we recover from the oil site is sourced directly from BP crude oil in a deep water portion of the Gulf of Mexico. So in today's visit, we also see a very nice stable isotope facility here in the Institute. And so we use the stable carbon isotopic system for the organic matter recovered from oil sediments. And this is very useful because those so much the organic matter, the carbon isotopic signature closely match the living plants, because those living plants die, they bury, so they should have very similar carbon isotopic signature. So in Florida, they are dominated by this needle-shaped C3 plants. So they have lower delta C13 isotopic composition. However, if you go to Louisiana, the heavily contaminated site, they dominate by C4 plants, and they have a very different, heavier stable carbon isotopic composition. And this is because C3 and C4 plants utilize different photosynthesis pathway. But why this is important, and especially for the heavily contaminated site, they have heavier delta C13 composition. And so in Louisiana, so previous study, they already analyzed the delta C13 for the so much plant, also the organic matter. We can see they kind of close to each other, slight variation. So in this study, we analyzed the BP initial crude oil and also the weather oil we kind of sample from scratch of the plants. And so you can see they are very close to each other. So that this information tells us that the stable carbon isotopic composition, just like other biomarkers, they do not change much when they are subjected to chemical weather. But the very good news for us is because this crude oil has very different carbon isotopic signature compared to the organic matter of the plants, these soil marches. So this histogram, we compare the carbon delta C13 composition of the crude oil, which has very depleted delta C13, and this natural plants has a more positive delta C13. So for the unaffected sediment, again, we should anticipate should have a similar delta C13 value to the natural plants. However, you can see that for the contaminant oil sediment, you can see a shift to the more negative values. So indicate the influence from isotopic depleted oil. And so in fact, we can use a simple mass balance approach to estimate or quantify how much pore spaces was replaced, contaminated by the inflow of the oil. And it's because we know the delta C13 of the 2N, the original plants, and also the inflow of oil. And so this just shows that with a different percentage of the pore spaces being replaced or occupied by invaded oil, you can see how much shift in delta C13 for the contaminant sediments. So this is also very useful provide. So we combine the geochemical biomarker versus stable carbon isotopic composition help us trace fingerprint the source and the weathering of the spillway. And so this diagram we shows the pH, also the hydrogen sulfide that show the depth profile. Again, the water sediment interface right here. So again, you can see an increase in pH and also a notable increase in hydrogen sulfides. And we believe it's because the inflow of oil will enhance the reducing, make the system more reducing. And so the natural sulfate reducing bacteria that we use the oil as organic carbons. So they will reduce sulfate, seawater has a lot of sulfate, convert to hydrogen sulfide. So this bacterial sulfate reduction will remove a lot of protons. So this kind of explains why we have elevated pH and also elevated hydrogen sulfide. The story doesn't end as a hydrogen sulfide because hydrogen sulfide can react with ferrous ions and form biogenic iron sulfide. So this is the image of those very small biogenic iron sulfide crystals, and this probably formed by the reaction between hydrogen sulfide produced by sulfate reducer with iron sulfides. And I'm going to skip these slides. So very important scientific question we try to address for this research is what happened to the trace elements during the oil spills. And so again, we separate pore water with sediments. We run the ICP-MS, including lesser abrasion ICP-MS, try to compare the level of trace element in the sediments versus those still dissolved in the pore water. And so what we discover is high concentration of the trace element found in this oil contaminated sediments. And so certain crude oil, they have a higher nickel contents. So you can see here a nice correlation between the nickel in the sediment versus the TOC in the sediment, especially for the heavily contaminated side. So I showed this image before, those biogenic iron sulfide. So we run a laser abrasion ICP-MS. You can definitely see that the spike for iron and sulfur kind of prove this is iron sulfide solid. But you also see other trace elements, arsenic, lead, zinc, mercury. And so if you look at the pore water, so all these trace elements, even though we see a high elevated concentration in the solid sediment, but in the pore water, they are very, very low. Only a few ppb or lower. And so we believe that this bacterial sulfate reduction, because of this biogeochemical reaction, they fix or lock most of the trace element into this biogenic solids. And so I'm not going to read through the summary. I think the lesson we learned from this research, first of all, we know that the spill oil, especially the heavy fraction, they still remain in the sediments. But their long-term ecological biogeochemical effect, I think, will still require further research. In terms of trace elements, the good news is most of the trace elements, because of the bacterial sulfate reduction, we see a significant sequestration. They are locked into the biogenic solids. But keep in mind those iron sulfide, their stability can change, especially when the water table fluctuates. Those iron sulfide is not going to be stable. For example, when the water table drops, introduce oxygen, system become more oxidized. Okay. And this is essentially the problem we see the arsenic in terms of the high level of arsenic is because associated with moderate reducing condition that the host dissolve and release arsenic back to the pool water. So it's a very complicated biogeochemical system, and we believe that we need to, if we get more funding, we'll be interested to go back to this site to look at, just to study the same system almost 15 years after this main oil spill events. I think I'll stop here. Happy to answer any question or comments you may have.
Thank you very much. The first part of your lecture, the main cause of the arsenic absorption is because of the seawater intrusion also?
Those are in the coastal area. If you move further inlands, if you look at the fluvial aquifers, and the arsenic is rich in the shallow depth range from about 10 to 30 meters. So if you go to the shallow unconfined aquifer, you go to the deeper aquifer under more reducing condition, arsenic is low. Only in this very narrow range, about 10 to 20 meters, why people hand drill. So each well, this hand drill well only costs maybe $20 US. Because, again, that's why the problem is so widespread, because that's that most of the village community, they can afford to drill the shallow well into this special redox zone under iron-inducing condition. So essentially, arsenic is mobilized by the bacterial reduction of iron oxides. And because of the large river, they also deposit a lot of natural organic matter. So those iron reducer, they fill on those natural organic matter, dissolve iron oxide, manganese oxide, normalize arsenic. But in the coastal area, because you also have the geochemical effect of the intrusion of the seawater, in some cases can make the case worse.
Into absorption. Okay. This is interesting about the second part, that the oil spill causes the fixation of the trace metals, right? So this is a solution for contaminate areas with metals.
So in fact, if you go to the natural unaffected wetlands, you probably can see similar biogenic iron sulfide. There's a lot of those coastal wetlands under reducing condition. So those are probably the bacterial sulfate reduction already occurred in associated with most of the coastal wetland. But then the concern for why the BP pay a lot of the money to recover the ecosystem. Again, the crude oil itself could have a lot of trace in it, including nickel, maybe others. And so also this can affecting, because of bioaccumulation of mercury, also other toxic trace elements. So the question is, for the community heavily depend upon the fishing tourist industry, and so the spillover bring additional amount of trace in it. So what happens is going to make the seafood even more unsafe to eat. But for our research, again, we're looking at both the pore water, groundwater versus the solid sediments. So it looks like, but this is only based on the data we sampled 8-9 months after the oil was showed. And majority of trace elements are sealed is locked into the solids. So in the pore water, it's still very low. So also we have, so in terms of, so like Zeki mentioned earlier, the toxicity mobility, that's why it's very important when we do this kind of research. If you just look at the total concentration of chromium or arsenic, sometimes doesn't address all the environmental health issues. For example, for arsenic 3 is more toxic in terms of the human. Also, when arsenic form aqueous complex with organic compounds, some medical experts say that they are more toxic than inorganic arsenic. So that's why for address also the mobility. So the difference between arsenic 5 and 3 is mobility. Arsenic 5 is negative charge anion, so they can react with clay, iron oxide adsorption. Arsenic 3 is a neutral species. They actually move faster from the groundwater, as greater mobility. So I think for any kind of scientific research address the environmental health issue, we need to be really carefully looking at speciations. Also, the different species have different mobility toxicity. I think chromium is the same here. Selenium, most of the trace elements. So the geochemistry workbench, the model I mentioned, they also has an ability you can essentially model the speciation under different EH, pH conditions. So EH, pH are redox sensitive, so you need to measure those parameters via the field site. And then you can use the geochemistry workbench to tell you what is the dominant species. They can tell you thermodynamically which one is the most stable, which one is the dominant species under different field EH, pH condition.
So thank you very much for the wonderful lecture. And so we can finish here the lecture.
So again, we are so impressed with your research instrument.
Okay, yes.
Like lithium, definitely. It will be really interesting if you have a capability to measure the isotopes.
It's going to be a collaboration, right?
Right.
Yes.
Especially we try to address the geogenic source from lithium, because they can come from different geogenic sources.
Yes.
Yeah, clay, igneous rock, brine, and the geothermal system.
Yes, this is the idea for the geothermal systems to trace this about the signatures of the leach and the bottom also, right?
Have you in the department, do you do any rare earth research, i.e. rare earths and
About the what?
rare earths and
I don't think so, but we have a colleague in Unicamp, the University. She is working with gadolinium in superficial water and groundwater to trace the contamination. But I don't know here
We have some colleagues that are working on pegmatites, I think.
Yeah. Pegmatites, which involves yeah, I think Brazil is the second largest nation with i.e. rare earth reserves. So a lot of potential there. So probably. So Jackie's lab now is being set up and we are able to analyze. I think for similar SCP and SU.
We cannot do our elements in water here, neither isotopes yet. In this project, we also want to do some iron and amino acid analysis in water. Also. I just have to think some other issues that we can collaborate with. I can see some.
Yeah, we also want to bring back the information you gather from this trip. Then we have a very strong group, especially geochemistry, hydrogeology. We hire new hydrogeologists, including myself. We have a group of 3, similar to your group, working on water-related issue with a strength in chemical hydrogeology, companion hydrogeology. So definitely we can explore the opportunity to work together.
We had the project with chromium, right? So sometimes we have this type of research, most with inorganic contaminants. Reginaldo works with organic contaminants, and the professor Reginaldo, but I don't know. Dailson also, another professor, works with organic contaminants. Our group, I think the main topic is thinking about the hydrogeochemistry, about anthropogenic contamination or natural contamination, but related with inorganic contaminants.
Do you also analyze emerging contaminant like PFAS in the house?
We have another colleague in Unifesp, another university, and she's also analyzing FAS. I don't know, together with what a machine? She's working with emerging contaminants.
But here is Reginaldo.
And this university in Reginaldo.
Because sometimes we receive some demands from enterprises or other places or problems that appears in the country, and they came to us to have to solve because we had some issues regarding also split of oil in northern Brazil. Federal police wants to discover if the oil that reached the beach is not from the ship that the government or gold. So sometimes they ask us, what can we do to study this? But it's not our main
focus.
But sometimes appears these problems, and knowing that we can collaborate on. ontologists, because we have, what can I say, it's a elite, we have an investigator, a federal police investigator here that is institute working in postdoc. And sometimes he has the most different demands or issues for us, and they need to have more scientific knowledge in solving these problems. So it's
oil tankers they are carrying the Brazilian oil.
sorry.
The oil tanker, the oil.
The ship that is traveling is not Brazilian. I think it's Venezuela.
Venezuela.
Yeah.
Maybe Dr. Lee was mentioning about that there's some biomarkers that
Yeah.
can be looked at that is really the origin of the oil spills that are coming from which countries or
This was the case of the Northeast. In time, it was 20 years.
I don't really.
This was a environment problem that was in the television. So, but I don't know if they finally discover who know into. Yeah, I don't know how is the enclosure about this phase. It's a mystery for us. But this is a nice approach here with biomarkers, of course. To know, but then we should know the signature of the biomarkers of the oil, the source of the oil.
They probably have it. I don't know. Now we're working with them to build a data bank for gold deposits in Brazil that could be used to trace gold used to launder money. Money laundering. When you, okay, so
Trace.
to trace the gold, the
source.
the criminals use to do this money laundering or money, I don't know. So it's linked also to cocaine traffic in South America, and they are putting this gold from
Kind of geographic trace.
areas or Indian areas. So they are extracting this gold immediately and put this gold into the market, and they want to trace the origin of this gold, if it's from which place in Brazil, or South America.
you have all the equipment here to get the fingerprint of the liquid. Correct, right?
Really, the sky is the limit. See a lot of very important scientific application.
Yes.
Yeah. Thank you so much. Yeah. Show us your lab.
Remember here that if you work, if you work with
Urban geochemistry, you work with
Geochemistry.
urban from the cities.
geochemistry, road sediments, particulate matter, street dust in urban areas.
In urban area.
Yeah, we
Oh.
work with this.
Because our, yeah. So you kind of interested in geochemistry of urban large cities. Well, Auburn, unfortunately, we have faculty working on stormwater. They analyze the trace element model contained with stormwater, but nothing like a big city like Sao Paulo. It's because of our location. We even though we are 1.5 hours from Atlanta, well, our focus is not much on Auburn. I know that with all the facility you have, you could do a lot of research for here is living contamination.
A month ago, I had a meeting with the stormwater workers, and the preliminary data, actually what Dr. Lee says, Auburn is very clean. So when I look at it, that preliminary data from stormwater, you could drink it, it's clean. Trace element contaminations is, everything is just a couple of ppb, and even lower than the ppb. So I think 6 to 8 months ago, another researcher approached us. It was from California. They want us to analyze the white tissue. Actually, what they did, I think, they're using a chem wipe or something similar to they're wiping the surface of the house or factory, whatever it is. They are collecting all the dust, whatever, in some certain size of the surfaces. And then, but we were going to analyze, but we couldn't. The reason that I believe that the material that they use for the wiping is not the right material, because they use the cotton fiber, and the other is the chem wipe. But the chem wipe, everything in it chem wipe, okay? And then we don't know about the concentrations of it's not a clean eventually. And then the fabric they use, cotton fabric, they have a microwave digestion unit, but I can't digest that because the big cotton fiber material, and we don't do any open leaching or open digestions in our laboratory. But what I found that there's a special fabric used for this wiping the surface, and this fabric is digestible, fully digestible, and also clean for the trace metals.
The air pollution is, I think,
Yeah.
a big city.
Yeah.
Probably air pollution.
Yeah. So then, if you haven't started yet, I'll be happy to share that, the information to you, that fabric, because fully digestible.
I'm a little worried about your flight,
Yes.
and because you need to go to Guarulhos, and
All the heavy traffic.
as we have traffic also, because it's a rainy day. This is the worst the worst scenario for São Paulo. But the flight is at 9 o'clock.
Thank you so much.
Oh, you're
Yeah.
very welcome.
Zaki, I also learned a lot from the equipment. I walked through
Okay.
all the installation.
So now we
But yeah, we share the information with our colleagues.
okay,
Yeah.
okay. But now we are in touch, and so again, for prospect some collaboration. I think it's
Great.
wonderful.
Thank you. Thank you.
Thank you. Thank you.